Hi everyone, welcome to Algorithm Seminar. Today we're happy to have John here to give a talk. He's a postdoctoral researcher at Stanford University working with Percy Liang. Previously, he completed a PhD at the University of Washington, advised by Sham Kakade and Zaid Harchaoui. His current research focus is to improve the capabilities and controllability of generative models. His work has been featured in media outlets, including TechCrunch and the Times of London, recognized by outstanding paper awards at NeurIPS and ACL, and supported by an NSF Graduate Fellowship and a Qualcomm Innovation Fellowship. Please welcome our speaker.
Hi, thanks for the introduction. Yeah, so I'd like to talk today about robust distortion-free watermarks for language models. And this is joint work with colleagues at Stanford, and in particular led by a graduate student, Rohith Kududapudi. So as generative models become widespread, there's a lot of interest in detection algorithms that attempt to identify content generated by these models. So you might be an educator who fears that students are turning in fraudulent work, or maybe a policymaker who wants to better understand the pervasiveness and distribution of generated content on the internet, or maybe people in the audience here, professionals at tech companies who want to deploy products responsibly and manage online platforms. But there's also an increasing recognition that these detection systems just don't work very well, and maybe fundamentally they can't work very well. If you think about it, when you're trying to build an AI detector, you're really playing an adversarial game with some very smart engineers who are doing their best to foil you. And the fact is that as these generative models that we're building improve, their outputs will look increasingly realistic, and simple detection mechanisms become impossible. So what can we hope to do? We need some leverage on this problem. And one way to get leverage is to apply a watermark to generated content. And watermarking is attractive because it makes the detection problem easy. The detector simply has to check for the presence of the watermark, and if it's there, we know that the content came from this system that applied the watermark. But traditional watermarking schemes also introduce distortion into generated documents. So we've all seen watermarked content that looks like this. And the idea of watermarking a generative model is similar. We want to somehow stamp the outputs of our generative model with an identifier that makes it easier to track the content that originated from that model. But I mean, the fact is that if we can't be more subtle about our watermarking mechanisms than this type of example, then no one will buy this as a solution. We need to be more subtle about this. So today, I'm going to pose the question and answer the question, can we watermark a generative language model without distorting its outputs? And again, we need to start by asking, where can we get leverage on this problem? So we're going to seek leverage on this watermarking question in two ways. First is that we're going to apply a statistical watermark. So the idea is we'll use a randomized algorithm to apply the watermark, which will and then we'll allow ourselves some margin for error. But ultimately, our goal is that we're going to try to take that error possibility and drive that margin of error very, very close to zero. The second and maybe more important leverage that we're going to apply to this problem, and this is really what's unique to this modern generative modeling setting, is that we're going to apply this watermark during the process of generating a document. So this setting is really quite different than the traditional setup for watermarking, which imagines you have a pre-existing image or a pre-existing text document and are somehow like post hoc after the document has been created, trying to stamp a watermark on it. And this fact that we're creating the document is actually going to give us a lot of leverage for inserting a subtle watermark into the text. Okay, so this is the setup. We're imagining we're generating a document. So let's just briefly refresh and get on the same page about what LLM generation looks like in the LLM inference loop. So the idea is we have this inference loop when we're generating text from a language model. And the idea is that we're going to iteratively call our model on a prefix of text that's been generated. And what the model is going to produce for us is it's going to produce for us a table of probabilities or logits that tell us the relative likelihood that each word in the vocabulary comes next following this prefix. And we're then going to choose the next word proportional to these probabilities based on some random number generator and repeat autoregressively. So early work on watermarking text uses this idea of a hash-based watermark. And this isn't like a real hash-based watermark that you would actually run in a production system, but just to give you a cartoon version of what a hash-based watermark looks like, let's take a look at this algorithm. So the idea here is that we're going to create a mask on the logits that our model produces over the probabilities of the next word in the sequence. And we're going to restrict the possible words that the LLM can choose to generate at each step. Specifically, in this cartoon example of a hash-based watermark, what we're going to do is we're going to mask out half the words that the LLM could potentially produce. And we're going to choose which half of the words based on a pseudo-random number that's computed based on a hash of the prefix of the sequence. So at every step, when the LLM produces the next word, half the vocabulary is off limits, and the half that's off limits is determined just by looking and computing a hash of the tokens that have already been produced in the sequence. And this idea was proposed by John Kirchenbauer et al. And appeared last year in some of the earliest work on watermarking a large language model. And to give you a sense of how detection of these watermarks works, well, we've essentially created with this mask a red list of words that at every step the language model can't produce. And our null hypothesis, if the text hasn't been watermarked, is that at every step in the sequence, approximately 50% of the words should belong to the red list. But if a suspiciously small number of words in a document belong to the red list, then this is evidence, potentially very strong evidence, that this hashing watermark had been applied when this text was generated. Okay, so this is the just kind of cartoon version of what some of this related work on hash-based watermarks can do to impart a watermark into generated text. What can go wrong? Well, we're changing the distribution of text that's generated by the language model here, right? We've at every step, we've ruled out half the words that the language model can produce. And this has the potential to affect the quality of outputs produced by this language model. So here's an example. Here I've taken a language model, Llama 7B, and I've prompted it to give me a list of 20 movies. And I'm going to apply this cartoon hash-based watermark during the generation process. So here's the list of movies that it gives me. And at first glance, this list looks fine. But if we keep going and ask it to generate more and more movies, we rapidly descend into chaos. We end the list with 7 repetitions of sequels to a movie that never existed. And to add insult to injury, we asked for 20 movies and it gave us 19. Okay, so fine. Clearly, we could tune the parameters of the system to distort less. Maybe we could make our red lists smaller. Maybe we could play other games with how we apply these hash-based watermarks. But I think there might be a sense from looking at this approach to the problem that there's a fundamental trade-off here between the detectability of a watermark and the distortion of the outputs of your language model to which this watermark has been applied. And today, I'm going to argue that this is not the case, that in fact, there's no such trade-off between detectability and distortion of the model outputs. So in particular, we're going to see how to construct a distortion-free watermark for text based on a secret key. And we'll see that this watermark is provably undetectable in generated outputs unless you know the key. So, okay. So it might seem surprising that this is possible. So let's just go through a simple sort of toy example of how this could work, and then sort of build up the framework of how we're actually going to apply a watermark and detect it with these guarantees. So let's suppose I've given my language model a prompt, like the hungry cat. My language model can complete this prompt, as we've seen, by iteratively predicting the next token in the sequence. But there's another piece of this picture that I haven't shown yet, which is that at each step of this process, the model must make a decision about what word comes next from many possible options. And these decisions are driven by a random number generator, or RNG. So at each step of the process, what's going on? Well, the RNG produces some die roll, and we use that die roll as an input to the LLM, which in addition to the prefix, the prompt that we're feeding to the LLM uses to select an output. And notably, this random number generator has a seed that's used to determine this sequence of, well, really pseudo-random numbers that come out of the RNG. So as a thought experiment, here's a very naive watermark. Let's just run this LLM with a fixed seed. We'll call that the watermark key. And now, if I want to detect this watermark, we can just rerun the LLM with the same key and see if we get the same result. Now, there are several major problems with this watermark. First of all, it makes our language model deterministic. It will always respond in exactly the same way to the same prompt. But there are other problems with this watermark too. So we often won't know the prompt that was used to produce the generated content. A user will prompt the language model, get some output, and then maybe their prompt is write me an essay on World War II, and they get the essay on World War II, and then they submit it as their homework assignment. So without knowing what the prompt was for the language model, we won't be able to apply this watermark. And the user might also be adversarial in many of these settings. They might crop or edit the output of the LLM, maybe adversarially, maybe not. Maybe they just fix some things up or change things to be more suitable for their needs. And we want to be robust to cropping or editing of the model's outputs. But this naive watermark also has a really nice property, which is that if you only run it once, it behaves exactly like the unwatermarked LM. All we did was pick a particular seed for running the LLM. We didn't really mess with its behavior in any way. And what this means is that, at least for one round of interaction with the LLM, you can only detect this watermark if you know the key. And we call this property the distortion-free property. So now let's see how we can create a better watermark that fixes some of these other problems that we identified, but that preserves this distortion-free property that we really like about the naive watermark. So here's our watermarking algorithm. What we're going to do is we're going to generate a long sequence of die rolls from the seeded RNG. And then we're going to choose a random subsequence of these dice rolls to feed into RLM. In practice, we'll see later that we can make this sequence of die rolls very long, like potentially millions or billions of die rolls long, which will make these subsequence collisions very unlikely. And as long as we don't get a subsequence collision where we pick the same sequence of die rolls twice, we'll have the distortion-free property over multiple interactions with the LLM. You can sort of think of collisions in this RNG sequence that we've pre-rolled as analogous to hash collisions in a hash tree-based watermark. Okay, so just writing this out as code, this is the distortion-free watermark, the application of it to generation. It's pretty simple. All we're doing is pre-rolling a bunch of random numbers from our RNG, and then using a random offset into that sequence to drive the generation process. Okay, so how do we detect this watermark? Well, we've created a bunch of problems for ourselves compared to the naive watermark. The first is that we don't know this subsequence of die rolls for the RNG sequence. We're also not going to assume that we know the prompt that was used to drive the language model. And we actually won't assume even that the detector has access to the LM itself, just to this watermark key, just to the seed that was used to produce the RNG die rolls. And finally, as we mentioned earlier, we kind of want to allow the user to make some modest cropping or editing of the output of the LLM. We want to be robust to that and still be able to detect the watermark, even if there's been some editing done to the outputs after it's been produced. Okay, so in the context of all of these challenges, let's see how we detect the watermark. So first problem, we don't know the subsequence of the RNG sequence. Well, that's actually okay. We're just going to search for all possible alignments of our text that we're testing with the RNG sequence. And we'll calculate the optimal alignment between these two sequences. Okay, second problem is that the user might have cropped or edited the output of the LLM. That's actually fine too. When we're calculating these distances between the RNG sequence and the text we're testing, we'll use a Levenshtein distance. So this is an edit distance that will be robust to some amount of substitutions, insertions, and deletions in the text that we're testing for the watermark. I will say, as an aside here, that this means the detection of this watermark is relatively expensive compared to these hashing-based approaches. So it scales with the length of this RNG die roll sequence, whereas the hash-based methods only scale with the length of the test sequence that you're testing. And as we've seen, we want to make this RNG die roll sequence quite long so that we minimize the chance of collisions when we're selecting subsequences of the RNG die sequence. So there's some tension here between the cost of running detection of this watermark and getting this distortion-free guarantee by using a really long RNG sequence. Okay, but the elephant in the room is that we also aren't going to assume that we know the prompt or the LM. And if we don't know the prompt or the LM, how are we going to detect correlations between one of these RNG die rolls and a word or token of text? It's not obvious how to do this. So to see how we're going to do this, let's think about how an LLM generates a word. So it takes as input this prompt that we're not going to assume that we know, and produces from that prompt a table of probabilities over each of possible next words in the vocabulary. We then use a decoder function that takes as input this table of probabilities and a random die roll and maps that die roll and the probabilities to a choice of word. So this decoder could be, for example, inverse transform sampling. It could be Gumbel max sampling. This is a function that pushes forward the randomness of the die roll to a choice of randomness distributed according to the probability distribution. But this decoder function itself is just a deterministic function. So that's all well and good, but we're not going to assume that we know these probabilities that are the inputs to the decoder. Well, why? Because if we don't need to know the probabilities, then we don't need to know the LM, because the LM was only used to produce this table of probabilities. And if we don't need to know the probabilities, we also don't need to know the prompt, because the prompt is only used as input to the LM to produce the table of probabilities. So not knowing the probabilities is going to be really convenient for us, because that lets us avoid having access to the LM or access to the prompt that was used to produce the text. But this creates a huge problem for ourselves, because now how do we know for a given die roll whether it would have produced this given word, in this case silently, if we don't know the probabilities that the language model would have assigned at this point in the sequence? So to understand how we can do this, we need to understand a little more about the structure of this decoder function. And as an example, let's use as a decoder inverse transform sampling. So actually, if you look at our paper, you'll see that inverse transform sampling is maybe not the strongest possible decoder. Gumbel sampling works better, but I'll be using inverse transform sampling here because it's a nice pedagogical example of how this works. So let me begin by giving a brief refresher on how inverse transform sampling works. So we have this number line here, and we're going to be looking at the unit interval between 0 and 1. And the idea is we're going to take all the words in our vocabulary, lay them down on this interval, such that the width of each word's bucket, its allocation of the unit interval, is proportional to its probability, or actually, in fact, equal to its probability. And then what we're going to do is we're going to uniformly sample a random number on the interval from 0 to 1. And the word that we choose is going to be the word associated with the bucket with the subdivision of the interval that this random number u that we chose falls in. So in this case, u fell in the bucket associated with the probability mass of word 3. So that means the decoder of the inverse transform sampling decoder of given probs and this random number u is word 3. So that's inverse transform sampling. Now, suppose we don't know the probs. We don't know the probabilities, so we don't know the width of these buckets. What can we do? Can we do anything? Well, it turns out that we can. So let's think about what happens if this u that we sampled is very close to 0, but the index of the word that we observed, w, is very close to the top of the vocabulary. So the index of this word is close to the vocabulary size. That means that u is way close to 0, but the bucket for p of w is really close to 1. In fact, the only way that we could observe word w having sampled the value u is if the probability mass of word w is so large that it stretches across almost the entire unit interval so that it picks up this value u over here, and all the rest of the probabilities of all the rest of the words in the vocabulary are scrunched up between 0 and u. So that's pretty unlikely that that would happen. And what this means is that in general, our observed word w and the random value u are correlated. You won't be able to know perfectly what word will be generated given a choice of u, but you can see that certain combinations of w and u are more or less likely than others based on the positions of the words in the vocabulary that we set out on the number line according to inverse transform sampling. So we can look at a statistic of something like u minus like 1 over vocab size times the index of a word and measure how distant those two quantities are, and use that as a test statistic for testing the correlation between this w and a particular value u, and compare that to the null hypothesis where this value u was a different draw from the uniform distribution. So this is how we're going to, this is the mechanism that we're going to use to calculate correlations between the random diagonals of a random number generator and the observed words of text that we've seen in a document. Okay, maybe I should stop here and ask if there are any questions. Have I completely lost everybody? Is there? People still here? I can't actually see any.
Maybe a quick question. So is the index of the words like randomized at every location? Like that?
Yeah, that's a great question. So for the theory in our paper, we do assume that the indices are randomized actually at every step. But in practice, you can just sort of pick an ordering and use it, and it's fine. I do think it's important. So what do we actually run in practice? We sort of pick a random ordering of the words once and for all, and just use that throughout. And I think this is important versus using, say, just like the ordering of the vocabs items in like the vocabulary file, because you can get weird things that could happen then. Like you could imagine like I don't know, it's like a multilingual vocabulary and all the English words are like first in the vocabulary. So then all the English words will be close to 0 and you'll get a much less powerful test than if they were sort of spread out evenly across the vocabulary. And then, yeah, like to do the actual theory and prove the math, we assume that you're randomizing the vocabulary lineup at every step of the process. But this is not necessary in practice. In practice, like just fixing a random permutation once and for all is fine.
I see. And do you assume you know the key to fix the like permutation or something like that?
Yeah, exactly. So how you would do this in practice is, so you have some like random number generator, and your watermark key is the seed. So you seed your random number generator. First thing you ask it for is to produce a permutation of the vocabulary, and then you ask it to produce this long sequence of uniform random die rolls, and the detector just repeats that process where they seed the same random number generator to get the permutation and the vocabulary items. Maybe I should also say that sort of like pseudo randomness is not really essential to this algorithm. It's more about a convenience for communication of the key. So you could, for example, use like a Geiger counter or something to produce this random vocabulary permutation and all the random uniform number variables. And that's fine, but then you have to share all of these random numbers with the detector. So you're potentially sharing like megabytes or more, which is maybe not terrible, but you have to share like all of these randomly generated quantities with the detector. Whereas if you're using a pseudo random number generator, you can just share like one 64-bit seed or 32-bit seed or something with the detector. And as long as you're both on the same page about what pseudo random number generator you're each using, then they can reproduce the permutation of the vocabulary and all of the random die rolls themselves without having to communicate that.
Thanks.
Yeah, but that's really, yeah. I mean, I think some papers play up this idea that like pseudo randomness is somehow essential here, and for most watermarking algorithms, I don't think it's really the sort of important point.
Could you do away with not knowing the vocabulary and instead kind of like learning these correlations on the fly, being like, well, every time I saw the word cat, it was like a small index. So, whatever. Cat is probably near the beginning.
That's a great question. Yeah, so like maybe in some future variant of OpenAI's language models, they don't even bother to tell you like what the vocabulary is. It's an interesting question. I mean, I think like at the end of the day, all of these watermarks require cooperation on the part of the provider, and I also can't imagine that even a paranoid company like OpenAI would see their vocabulary as like, secret proprietary knowledge that they need to be defensive about. So I think that requiring the provider to specify the vocabulary is like a reasonable thing to ask. But yeah, maybe something could be done if you didn't know the vocabulary. I guess yeah, I guess I would need to be convinced that it seems like this is like sort of reasonable to ask the LM provider to tell you what the vocabulary is.
I see. Yeah, I was thinking like in a setting where the vocabulary changes over time or something, like you could imagine maybe you have a fixed decoder and a fixed like random number generator or something, with the starting seed. But,
yeah.
You're like, oh, am I using v3.9 of this, LM or like whatever, right? Like maybe they'll change the vocab behind the scenes and not really tell you. I don't know.
Yeah, no. Okay, but I think this is the more important question, which is that this is, I mean, very specific to like a particular language model, and if you're running this in practice, and like I think actually, I mean, this is sort of speaking, I think, to the broader sort of social technical question about how you might want to use these watermarks, which is at the end of the day, people really want the AI detector. They want to say, was this text generated by a language model? And watermark doesn't quite answer that question. A watermark answers, was this text generated by this particular language model? And it actually only answers that question if the provider of that language model was good enough to watermark it for you, which we haven't managed to convince any of the major LLM providers to do yet. So yeah, I mean, in practice, if you have different versions of language models in different vocabularies, then probably what you want, there probably won't be that many of them, to be honest. And then you just do a union bound over testing for each of the watermark, supposing that it's each of these different major LM providers.
Thank you.
Okay, so let's take a brief look at how these watermarks look like in practice. So here we've just grabbed the open Llama 7 billion parameter model, and we're using an RNG sequence length here of 2048, which is kind of low. I promised you can do millions. I promise you can do millions. But for here, this is a kind of a nice sequence length to look at, because this is the context length of the Llama 7B model, which means for any individual interaction with this language model, if you prompt it and get a response, it will be distortion-free because your RNG sequence is long enough that that however much content the language model provides, you'll be using fresh spirals from the RNG. So using this setup, we can detect the watermark in under 20 tokens of text with a pretty reasonable p-value. We can actually detect the watermark after altering up to 40% of tokens in a 35 token sequence, again, with a pretty strong p-value. And we can even detect the watermark after we do a round trip translation of like 50 tokens of English text into French and back to English again, with sort of comical p-values. And if you think that this is like maybe some fluke and that, oh, this only works because English and French are pretty similar languages, we actually did this with Russian too. And it works there as well. Like maybe you need 60 tokens to get this strong a p-value for Russian. But yeah, so I can refer you to the paper if you want more details on what these detection rates look like in practice. But I mean, I think the first order observation about the power of these watermarks is that they're tremendously powerful, and you really can imagine like running these watermarks on short snippets of text of the type that does appear on the internet, and catching the watermark with a reasonably reliable strength. You can even imagine like, okay, so like p less than 0.01 might be a pretty good p-value for sort of doing a broad analysis of like the amount of watermarked text on a social media platform, where false positives aren't maybe so terrible. But p less than 0.01 maybe isn't a strong enough p-value for accusing a student of teaching in a class with 300 students. In fact, you almost certainly get false positives in that regime. But remember, this is 20 tokens of text. And so actually what we'll see next is that if you're willing to even look at like 30 or 40 tokens of text, you can very, very quickly get really comical p-values, like p less than 10 to the minus 6 or more. And let me just now sort of jump to why that is. So essentially, what we see in the theoretical analysis of these watermarks is that the detectability of the watermark increases exponentially in the text length. So the more and more tokens of text that you observe, you become exponentially more confident in this test for the watermark. But on the other hand, detectability only decreases linearly in this RNG sequence length. So this is, remember, I was telling you earlier that this RNG sequence that we're using to seed the watermark can be made to be like millions of tokens long. Well, that's because like basically in sort of the analysis of the detectability of the watermark, it has a log out in front of it. And so you can really make this RNG sequence length really as long as you're willing to pay for the cost of detection, without really sacrificing very much in the power of the watermark. There is a caveat here, though, which is that low entropy sequences are hard to watermark. And this is actually a pretty fundamental observation to distortion-free watermarks. So the right way to think about this is think about what happens if I prompt GPT-4 to recite to me the Declaration of Independence. If GPT-4 is behaving, it will do this, what I've asked it to do, and recite it verbatim. And of course, the text that it outputs won't have a watermark because it's just the Declaration of Independence. So I've asked it to do really a zero entropy task here. And as such, the words that it's spitting out at every step will have zero correlation with the random die rolls that are driving the generation process. And so there will be no detectable watermark in the outputs. And depending on how you're thinking about a watermark, I actually think that this is really probably the right behavior. Like, this is sort of what you would expect a watermark to do, in the sense that sort of the more creative choice that the LM has injected into the generation process, the stronger the watermark should be. And the fewer choices that the LM is making, the less entropy there is in the content it's producing. Like this sort of seems like this is the watermark behaving as it ought to. And in fact, this is also, as I said, like a very sort of fundamental caveat, in the sense that we can actually prove a lower bound on the behavior of any distortion-free watermarking scheme. And it should be sort of intuitively obvious why there would be that lower bound, because again, of this example of the Declaration of Independence, which doesn't really have anything to do with how you're watermarking the language model. It's just sort of a fundamental fact that if you've asked it to produce unwatermarked content, it's going to produce unwatermarked content. Okay, so where are these claims coming from? Well, we get these theoretical analyses of the watermark that essentially look like this one. And maybe let me also just like back up a little bit here and just comment on how amazing it is that here is a problem that we can look at related to large language models that for which we can give like sharp theoretical analyses, which is almost never the case for anything involving deep learning. And the reason is because we're sort of able to abstract away the LLM, because we're looking at these correlations that don't sort of depend on the inner workings of the LLM or the tables of probabilities that it produces. And so we're able to give these really sharp analyses of the behavior of these watermarks, despite the fact that there's this very difficult to tame monster hiding underneath the bed in the form of the LLM that we're actually applying the watermark to. Okay, so what do these analyses that we give look like? So they're an inequality that looks like this, that bounds the p-value of the detector that the detector is producing. So this p-value is the p-value under the alternative hypothesis that the text is watermarked. This value n is the length of the RNG sequence. So this is this sort of how long is our source of randomness that we're using for the watermark. M is the length of the text to be watermarked. And here we see that as I promised, the p-value only increases linearly in this length n of the RNG sequence, but it falls exponentially in the length of the text that we're testing for the watermark. So, you know, if we're just willing to look at a few more tokens of text, we can very, very quickly turn a pretty strong p-value for the watermark detection into a comically small p-value for watermark detection. And the only way that these analyses depend on the underlying language model is in this term alpha. So alpha of text is what we call the watermark potential of the text. And what this is 1 minus the sum of the probabilities of the next word given the history under the language model. So this is exactly this comment that I made on the previous slide about low entropy sequences being hard to watermark. So if the probability of the next word in the sequence at every step is 1 or very close to 1, then this watermark potential will be very close to 0. And what that means is that inside this exponent, you're sort of scaling your length of text by this watermark potential of the text that you're producing. And in the extreme case, where these probabilities of next word are all 1, and therefore the watermark potential is exactly 0, well, then you've got nothing. then this bound is vacuous, and you really have no power to detect the watermark. But even in a low entropy situation, like code generation is famously like a low entropy generation task. As long as the language model is making a few choices every once in a while, if you look at enough of this text over a long enough sequence, eventually the p-value will start to drop. And over a sufficiently long sequence, you will eventually get a quite strong a quite strong p-value for the detection of the watermark. So that's pretty cool. Now that we've sort of seen the watermark, we've seen some empirical and theoretical results that sort of help us understand the behavior of this watermark. Let's now revisit these hash-based watermarks, which are more common in the community. So as I mentioned earlier, one like clear downside of our watermarking protocol is that the computational complexity of this detector scales in the length of this RNG sequence rather than the text length. And this RNG sequence we're going to want to make very, very long to get this distortion-free guarantee, even for a system that's under heavy usage. But on the other hand, these distortion-free watermarks break the trade-off between robustness and distortion, which is kind of awesome. So these hash-based watermarks, they typically hash based on like an n-gram prefix of the sequence. And essentially, if you make n longer, so you look at like a longer prefix before the first word and use that to seed your hash for determining the randomness for the next word, then the larger you make n, the less distortion you will get in your watermarking protocol, because you're less likely to get hash collisions on your n-gram prefix, but also the less robust you'll be to edits of the system. So if the user is editing like order 1/n tokens in the text, and you're looking at a hash of n-gram prefixes, well then most of those n-gram prefixes will contain an edit, and then they'll hash to something different, and you won't be catching the watermark in most of these windows of text. Whereas our watermarking protocol really has no trade-off between distortion and robustness. You have no distortion and a good amount of robustness. I'd also like to give a shout out to some concurrent work with ours by Miranda Christ and others, which takes this hash-based strategy and actually sort of pushes it to its limits to give a similar kind of guarantee to our distortion-free guarantee. So they call this an undetectable watermark. And they essentially use this hash-based scheme, but they, instead of doing like this red list, green list thing with it, they do a much more clever thing with the hash for getting the next token. So you get something that looks like a sample from the language model. And then they sort of adaptively adjust the length of this hash to sort of control for hash collisions. And so you are able to push these schemes, but of course they end up being not particularly robust, right? Because these prefixes that they're hashing on adaptively end up being pretty long to get their undetectability guarantee. And then if anything has been edited in that prefix, then you won't catch the watermark. Okay, so that's sort of the current state of play with our watermark and with hash-based watermarks. And just like,
can I ask you a question?
Yeah.
So what about the strength of the watermark? It's like if you plot like the p-value for 20 token sequence for them, I guess they will be higher. The p-value will be stronger, right? For those.
I don't know because they didn't run experiments.
They didn't run, but some of them run experiments, right? Have you compared with them?
Yeah, there may be some newer ones that run experiments. I haven't looked closely at sort of the state of the art. Oh, is this a question about Christ's work or a question more generally about p-values?
I'm assuming Christ's work, but I know they don't run experiments. But maybe others is also good. So
this is a great question. Yeah. So in general, for watermarks that allow distortion, you can always beat our p-values just by kind of picking a degree of distortion that gets the p-value that you want. In particular, like in a low entropy, or like we'll say in a no entropy setting, right, our watermark has no power, whereas a distortionary watermark will just produce the wrong answer and get a p-value. Yeah, one interesting question is, yeah, so actually, like, I guess one comment I would make about this is that you can combine these watermarks. So you could, for example, use our watermark and like a red list, green list, Kirchenbauer style watermark and combine the watermarks and sorry, yeah, I mean, if you're concerned about the power of the watermark, and especially like in these low entropy settings, you could just use both. I think in general, like, it's not quite comparable because you're in the distortionary case, because once you're allowed to distort, you sort of get to pick what you want your p-values to be at like a given text length, and just pick the amount of distortion. In the undetectable setting, in the distortion-free setting, yeah, I don't know, because yeah, like they didn't have experiments, and I haven't looked closely if anyone since then has run these competitively head-to-head.
I see. Can you go back to the previous slide a bit?
Yeah.
So, yeah, I know you defined this watermark potential.
Yeah.
I think other papers also define similar quantities, maybe some mean entropy, things like that. Is there a fundamental difference, or it's just like you want to calculate with this?
I would be surprised if there's a fundamental difference. I think yeah, this was just the convenient quantity for I mean, this is basically like, okay, like what's the difference? Like is there a log inside the sum or not? Why?
Because log would be more natural because you are taking the exponential and you get a probability. So the exponential would have a log probability that's more natural. But this one is more like approximation of that something, but just asking.
Yeah, no, I share your intuition that it seems like the entropy is the right quantity, and yeah, maybe our analysis isn't sharp.
Okay.
Yeah. I certainly don't have like an intuition that this is the right quantity to be looking at as opposed to the entropy. It seemed, if I had to guess, I would guess that the entropy is the right quantity.
See, maybe this is not a very fair comparison. I know this OpenAI, Scott Aronson, they have this blog post describing some mechanism, but it's not fully public. But have you compared with that or any connections?
Yeah. So I think what they're doing is actually pretty actually I don't just think, I'm quite confident that what they're doing is basically the Miranda-Christ's mechanism.
I see.
So this is they're hashing and they're adjusting the window of the hash to get a guarantee that there's a certain amount of sort of entropy in the n-gram you're looking at, so that you don't get collisions, and therefore can give a guarantee that you're but actually, I mean, like theoretically, all these results end up basically being the same thing, which is basically like, yeah, I guess, okay, and this is the question, like, okay, squared entropy-like quantity in the exponent. Yeah. So I think that they're fundamentally the same result in terms of power, and then yeah, the question I think, like, so one interesting question that I think that our method shines on is the robustness question. Another interesting theoretical question is whether you can improve upon this, like entropy squared or potential squared in the exponent. Like, could you improve upon the exponent in that quantity, which would obviously be nice. There's a paper I saw that doesn't have, I think, particularly convincing results, but does talk about like trying to improve upon that exponent, and that would be pretty interesting if that's possible.
I see. Just one. So like the robustness come from the added distance thing because you compute more quantities and stuff, right?
That's right. Yeah. We get robustness from the added distance, and it's not obvious to me what the analog of that would be in the hashing based setup. Like one way to think about our setup is like we've essentially created like a one-time pad. Like this is a very, very big one-time pad. And so you can think about like that RNG sequence as being like a budget of tokens. And you know, like if once you've consumed that budget, well, then you don't have the distortion-free guarantee anymore. And yeah, I mean, like you could also like you can imagine a protocol where like you sort of know what your daily usage is for your language model and kind of set the pad to be about that size, and then sort of consume your budget every day and cycle the keys. Cycling the keys is okay because you just union bound over all of the days that you've been running this, and it doesn't matter because that union bound is happening outside the exponent. So it's just sort of, yeah, you're basically just like growing your RNG sequence you're just sort of like n times number of days that you've run this since inception, which is fine.
I see. Thanks.
Yeah. I should probably wrap up as we're towards the end here. So let me just say a little bit about future work. So I'd be pretty interested to see if it's possible to resolve this tension that seems apparent between these three desirable aspects of a watermark. So in particular, in our work, we showed that we can sort of resolve this apparent tension between robustness and distortion freeness, which is pretty cool. But we introduced this kind of third axis in our work, which is detection complexity, where we're now materially worse on detection complexity than the hashing-based approaches. And is there some like ideal watermark that resolves all of these trade-offs and gets you fast detection with robustness and approximate distortion freeness? So that I think is a pretty cool thing to think about. Another thing to think about is just, is it possible to design a more powerful hypothesis test? So nothing about our work claims that the strategies that we proposed were optimal. And I'm curious how far you can push this. In particular, I think like one thing that's ripe is like we looked at two different decoder functions. We looked at the Gumbel sampling and we looked at inverse transform sampling, which I talked about today. And Gumbel is just much better. Now, okay, so there's two different decoders and the Gumbel sampler like seems to impart a much stronger correlation between the random inputs and outputs than inverse transform sampling. I mean, are there other mechanisms that you could use for mapping random, for pushing forward random randomness to samples from the model? And could these other mechanisms impart an even stronger correlation and therefore allow us to construct an even stronger watermark? Is not clear to me, but it seems suspicious to me that we looked at two and one is better, that maybe neither is optimal. All right. Happy to answer more questions. Thank you very much for coming today.